Oh, we'll try that again with sound. Good morning.
Good morning.
Okay. Today we're going to, today we're going to go into a little more detail on some of the process of the virtual reality and how it works. And we've talked about it being a probabilistic reality, and we will explore that just a little bit. But the good news is that the time we get to lunchtime, we'll be just about done with all the technical and so just the last, just this morning yet is the kind of the last part of this more technical part. And then after that, we'll be into experiencing again after lunch. And then there'll be some serious time for questions. I know it's very frustrating to be out there and have these hundreds of questions come up and no time to ask them. So hopefully we'll have at least an hour, maybe 2 hours later this afternoon to spend on questions. So keep in mind what it is, where your sticking points are, the things that don't seem to make sense and you need a little help with. Because we will have some extra time today for the questions. And then again, we'll have a lot of time on Sunday for them. Okay, next slide here. Can we change slides? This one's a little bit stuck. Oh, there they are. Okay. I'm not so sure we're the same there.
No, it's in the same.
Is it the same?
No.
No.
Yes.
Okay. We're good synchronized. Okay, we're going to talk about how we simulate our reality. Okay, let's say particle models require an absolute belief in materialism. Particle models being your standard materialistic reductionism. Okay, that means that everything starts with little tiny elementary particles. And as time goes by, they're getting more, we're getting more and more of those elementary particles. I think we have something like 61 particles now that are in the standard model of particle physics. Those particles are at the very base, and everything else is built up of particles. So you take the elementary particles and they make up things like electrons and protons, which make up things like atoms, which make up things like molecules, which then make the stuff that we experience. So everything is built from the bottom up. It's a bottom-up view. You start at the very bottom and you have to build up to this. And we're going to see that that is an extremely inefficient way to run a simulation. Also, it forces the philosophy, I guess, of determinism. If it's a bottoms-up model, then everything is dependent on those little particles. And this is why most scientists believe there is no free will. Most scientists are determinists, and they get to that because of their model. When you have a bottoms-up model, if you knew all of the particles, where all the particles were in the universe, and just what state they were in, what velocity they had, what energy they had, if we had all this information, then everything else from that point forward could just be calculated, you see, because the particles move, they interact, they do what they do, and we have the physics to understand that, and then that turns out to be what we are and what we do because we're built up of all these particles. So when you have a materialistic view, which is a particle model, then you also have, by default, determinism. Because it's not us that are making decisions, it's all the little particles that do whatever they do that turn up and make us, you see. So scientists are kind of stuck with this concept of determinism because of their belief in a material reality, which is, I guess, unfortunate for them because our experience tells us we do think, we are rational, we do make choices. That's what our everyday experience. So scientists, when they meet with that data that we are conscious, and you can't have consciousness if you have determinism. There is no consciousness. There are no choices made. You are not rational. It's like, it's just a movie. Everything happens because it's determined to happen because that's what the particles are doing and how the particles interact, you see. And when you talk to a scientist and say, yeah, well, what about this? You know, we've had an intent to talk to each other, so we're doing it. Or, you know, I could turn around and walk off, and we have decisions. And because they really don't know how to explain that, they give the easy answer, which is, well, we just think we have free will, and we just think we're making decisions, and we think we're, you know, interacting, and we have a free will, but we really don't. Well, that's like magic does it, you know, is how that answer is. Which is the magic does it is kind of the scientist's view of God does it on the opposite side of the spectrum. Well, you're going to see in a particle view, there's an awful lot of that magic does it inside of physics. Okay, now a virtual reality can be either deterministic or probabilistic. When we make a virtual reality or a simulation, if I'm going to simulate a rocket flying through the air or an airplane or something like that, I simulate it by writing down all the equations that govern that sort of thing. You know, the gravity and the pitch and yaw of the plane. And if I have a radar from the airport looking at it, then I do the electromagnetic fields. And that is a deterministic model. If I do all that exactly, then I have a deterministic model. If I have the exact same airplane flying the exact same way, I'll get the exact same answer out of that model. It'll always repeat the exact same thing. And if it's a really, really good high fidelity model, then I've got all the physics calculated, you know, to 5 decimal places, and I haven't made any shortcuts. So we call that a physics model. Okay? And they're very accurate. We can tell just what happens to that plane if a wind comes up, or if, you know, a rudder fails, or something like that. We can simulate that very accurately. That's a deterministic model. Now, there's another way to model that airplane flying, and that's a probabilistic model. So instead of actually modeling the atmosphere to find wind currents, we just say there's a probability of a wind current happening, so, you know, once in every hour and a half, which is the average for, you know, wind currents, we'll just make one happen. That's just probability. So now I don't have to calculate where all the molecules in the atmosphere are so that I can determine when a puff of wind comes by. I just probabilistically produce a puff of wind every so often, which is sort of what happens, you know, in the real world. Now that's a probabilistic model. And you see that's not so accurate because we're just claiming that what's going to happen to that plane is kind of what usually happens to that plane, rather than being a deterministic. That's the difference. So in making simulations, we generally try to use deterministic models because they're more accurate. But they've got a downside. They require a huge amount of processing. If I'm going to track all the molecules in the atmosphere for 300 miles or 1,000 miles all around to decide when a puff of wind's going to come by, you see I have a lot of calculating to do. I have a lot of particles to keep track of to do that. So it's this huge processing problem, whereas if I have a probabilistic model, I just reach into a probability distribution and pull out an answer, and there's either a wind current right now or there isn't, based on the probability. So that's very simple. But there's an accuracy issue. The deterministic models are more accurate. Probabilistic models are easier. And of quicker. That's the general idea. Okay, with a probabilistic model, you need a probability distribution of how the reality works. In other words, you need to know how often a puff of wind comes by. So somebody has to go up and measure wind and do that for a long time, and then take averages and do statistics and create a probability distribution that's accurately describing, those puffs of wind. So you have to take the trouble to make good probability distributions. Now, if your probability distribution is very, very accurate, then it requires a whole lot of time and data to make that probability distribution. Now you're back into a lot of computer time again. So I'm just giving you some of the trades of how that works, and we're going to take a look at these two possibilities. Okay, I'm going to talk about an example, give you an idea of how these things work out. We're going to take a very simple physical structure that we can describe both deterministically and probabilistically. And this is probably simpler than most. The more complex it is, the harder the deterministic simulation becomes. So you have very complex things, then there's lots and lots of particles to keep track of, and lots of interactions in order to determine what happens at the macro level. So this is something very simple, very easy, and yet you'll see there's probably 10 orders of magnitude difference between the effort it takes to compute the deterministic model and the other one. So let's talk about just a cannon, an old cannon, simple cannon, back 1700s kind of cannon. Now that's just a cylindrical tube, and you have this tube and you put gunpowder in, you push that back, and you put some paper called wadding in to make sure the gunpowder stays back there, and you push that in with a rod in through the barrel. Okay. And then you put your cannonball in, and put it in and let it roll down against all of that. And then you take a fuse, which is a piece of cord, a piece of rope, if you will, that is soaked in a gunpowder solution, and you stick that into a little hole. I think you all know about how the cannon works, down into where the gunpowder is. Then you light the fuse, it burns down, it lights the gunpowder burns rapidly, which expands, creates very high pressure. The high pressure pushes the cannonball out, and the cannon fires. Okay, then the cannonball goes someplace and lands. So that's a very simple machine, if you will. Not a lot of moving parts. Okay, now if we do this in a deterministic simulation, we have two things to consider. We have interior ballistics and exterior ballistics. Interior ballistics are everything that happens inside the barrel of the cannon. Okay, when you light that fuse and it burns down, it will ignite the gunpowder. And when it does, things get busy down there as far as particles go. Okay, the gunpowder lights. It'll probably burn unevenly. It won't burn perfectly. What's on top burns first, which then scatters the rest, and it will build up a pressure. And that pressure has to be defined in terms of particles. There's all these atoms, all these molecules down there trying to get out, but the gun barrel holds them in, and it builds up pressure. The pressure pushes against the ball starts to move, but the tube is not perfectly round in its cross-section. It's got imperfections in it. There's lumps and grooves and all sorts of things. So gas leaks out around it, and the ball starts to roll out, and it accelerates and picks up speed. But the calculation of this process of interior ballistics is exceedingly complex, because you have to do it at a molecular, perhaps even atomic level. You need to know where all the 10 billion particles are, how they're interacting, how that gunpowder burns as a function of time, because for us it looks like it's instantaneous, bang, and it's over. But in the physics problem, that's a long process that has to go on as one grain of that powder, interacts with the grains around it and so on. So it's an extremely difficult calculation. Matter of fact, it's so difficult that a supercomputer today would probably spend hours just burning the gunpowder and moving the ball out of the cannon. Hours. Supercomputer. Very difficult to deal with that at a molecular and atomic level. But that's what you need to do a deterministic calculation. Then the ball would exit, and when the ball exits, actually the barrel flexes a little bit. Yes, it's steel and thick, but it flexes a little bit. And how it exits out the barrel has a lot to do with the shape of the ball, which isn't really perfectly spherical, because you can't make anything perfectly anything when you build it. It's got its own imperfections. And it launches not exactly in line with the barrel, but a little up or down or to the sides. And as it goes through the air, there are air currents, little small air currents here and there. The ball will probably be turning because it is asymmetric. And as it turns, it piles air up on one side and pulls air from the other, which moves it one way or another. And so on it goes through the atmosphere. And as it moves, there's slight variations in gravitational pull, depending on what it's going over, whether it's rock or dirt or other things. See, deterministically now, we've got a hugely complex problem that would probably take that supercomputer to do the whole thing, maybe a day. It may even be impossible because scientists don't have enough information to model these things that accurately. So we've simple little machine like that, and we've just about made it impossible for scientists to do it deterministically. It's too hard. It's too hard a calculation. And then the cannonball lands someplace. Okay, and that's where it lands. Now, if you fire another cannonball right after that, will it land in exactly the same place? No, because all those things are different now. That powder was put in there with with the rod. It's configured differently. The wadding's different. The ball is not the same. One. It's a different one. The barrel now is worn a little bit because it just had the cannonball go through it. The barrel's a little different. The gas will escape differently. It's a totally different problem. Second cannonball, again, a supercomputer, if the scientists did have enough information to do it, would have a real hard time computing this one simple thing. Now let's take let's do that again. So then you fire another one. They're all different. That's called the ballistic dispersion. So when you fire these cannonballs, one of them will land here, and some of them go a little farther, some of them are shorter, some are to the right, to the left. They make a pattern out there in the ground. And if you fired 1,000 of them, you could look at that pattern they made on the ground and do a statistical analysis of it. And you can say, okay, most of them are within here. There's a certain probability that it's, this range, this kind of a circle around the center of all the hits. So you could say, it's a certain probability to be within this circle, within that circle, different probabilities to be different places, and now you would be creating a probability distribution of the result. But if you fired 1,000 of them, everyone being different, the gun barrel wearing as you fire them, the whole thing would tend to change to a bias as you went on. You see, you wouldn't be like firing, the same one again and again. You can't do that. Even if you had a new cannon, every time you brought in a new cannon and fired it the first time, they may be a little closer together, but you'd have a statistical description. Okay, now you could take that statistical description and make that your model. And if that were your model, then in this simulation of a cannon, you'd say, okay, the cannon fires, where does it hit? You'd go to your statistical model, you'd go in with a random number that says, well, it's going to hit, certain probability it's going to hit in this circle, or certain probability it's going to hit out here, certain probability. You'd go up and you grab one of those, and that's where it hits. Calculation can be done in a microsecond. All you need is that probability distribution. But you say, well, that still was a lot of trouble getting that probability distribution. You had to fire all those cannons. But now when we're talking about a virtual reality, that's a virtual cannon. That virtual cannon is being fired with virtual gunpowder, and the whole thing's already being calculated according to the rule set by the larger consciousness system. And the larger consciousness system does that very, very quickly, much more quickly than even our most supercomputers. And it can do that as often as it likes. Why can it do it as often as it likes? Something we haven't discussed yet is that the time in this virtual reality we talked about was that delta t. The simulation goes around every delta t, we implement or we increment time in the simulation and recalculate it. Okay, well, that delta t is big. In other words, it's a lot of time between delta t's for this virtual reality compared to the time in the non-physical. Okay, within consciousness has a much faster clock. So if you are consciousness, if you're doing the computation for this virtual reality, you've got lots of cycles, lots of computational cycles. Actually, something like 1 billion computational cycles of your own between every delta t in this virtual reality. So you've got lots of time. Tremendous, if you think in terms of computer cycles, you've got years. You've got lots of time to compute between every delta t in the virtual reality. We didn't talk a lot about that, but that's the structure. Every time you go down a level, there's about a billion cycles between levels, and that's in the books. But anyhow, so the virtual reality computer has lots of time to compute what's going on. It's virtual cannon, virtual gunpowder, virtual ball. So all that stuff is part of the virtual reality generated by the rule set. The rule set can work down at the particle level if it needs to. See, the rule set has all that physics at the particle level, at the deterministic level, we'll say. It's got the rule set that lets us evolve, which means all the details. More of the details than our physics has. And it can calculate those cannon shots by the millions to produce a probabilistic description. Not just by firing 1,000, but by firing millions. And it can do it between our delta t's if it wants to, from one of our delta t moments to the next delta t moment. So you see, it can create very accurate probability distributions, very accurate. So that's like the difference between those two approaches. Now, the probabilistic approach is a top-down. It's not all the particles creating the reality, building it up from the bottom. It's the larger consciousness system creating probability distributions that are just as accurate as it needs, no more. No sense doing something more accurately than necessary. So if this were a civil war or a war back in the in the 1800s with the cannon going on, then that would be a virtual war in a virtual reality, right? With a lot of virtual avatars being played by consciousness that's in the non-physical. Then every time a cannon was fired, a virtual cannon was fired, a virtual cannonball left, then there would be some probability of where that cannonball would land, and a random number or a random draw would be taken from that probability distribution, and that's where the cannonball lands. And if somebody happened to move their avatar right into that position, then that would be bad luck for them. If it just happened to hit a tree, then whatever, but again, it's all probability, you see. So that's the difference between the two models. One is extremely efficient, and the probabilistic model is extremely efficient and also extremely accurate if you have extremely accurate probability distributions, which you can have because the larger conscious system is working all sides of the problem. Everything that happens here physically is virtual, and it has the rule set. It can compute probability distributions. All right, let's go next. So we're going to compare now this bottoms up with the top down, so you get a sense of the two. Remember so we're going to do bottoms up first. In a bottoms up view, elementary particles are fundamental. The word fundamental means they have no cause. That's what we were talking about before. All the fundamental things have no cause. Time has no cause. Charge, mass, these things are causeless. They're fundamental. Well, with particles, it's like that too. Once you get down to the smallest particle, and it's called fundamental if it can't be taken apart, it doesn't have pieces. As long as it has the piece parts, it's not fundamental. So if you can take an electron apart into quarks, then the electron's no longer fundamental, but the quarks are fundamental because you don't take the quarks apart. If you could take a quark apart into other particles, then the quark wouldn't be fundamental, but those particles you take it apart into would be. So fundamental particles are the particles that don't have pieces. Fundamental particles have no causal effect, they just are. Okay, so we start with an assumption that we have hypothetical particles. Okay, and that everything's built up out of those particles. Now, bottoms up logic. So we start with the assumption that the micro world, and again, there's about 61 hypothetical particles that are models in that what's called the standard model of particle physics. Okay, those 61 hypothetical particles are based on 19 arbitrary constants. Arbitrary means that the constants were just picked so that the answers would come out right. Okay, we have answers, we have measurements, and we know this has to be the answer, so we multiply them by a fudge factor or a constant in order to get them to give us the right answer. And when we do that, we construct a physical world out of these hypothetical particles during which a mysterious process we don't understand somehow creates consciousness. And then we come up with a bottoms-up worldview that can explain a very limited set of objective physical facts about the physical world. And it's all based, of course, in the beginning on a belief in material reductionism. Reductionism means the material stuff keeps being reduced down to lower levels of particles. All right. Consciousness, of course, is a hard problem, and particles that have no beginning, that just are, is a hard problem. Hard problems are problems that create paradoxes. We don't know how it gets that way, it just is that way, and we have to accept it. Those are hard problems. This is an observation that in fundamental science, a hard problem is almost always the result of trying to justify an erroneous belief. In other words, if you have a hard problem, it's because you're looking at it the wrong way. You need a different paradigm in order to resolve that hard problem. Hard problems tell you that there's a problem with the way you're viewing. Okay, so like a dinosaur is a hard problem for fundamentalists that say the world is only 7,000, the universe is only 7,000 years old. So then you find, a million-year-old dinosaur bones, and that's a hard problem for them. You see? So hard problems generally mean that you have an erroneous belief where you have a hard problem. Okay, the origin of the Big Bang, where does that ball of plasma come from? That's a hard problem. Okay, elementary particles and all that we've talked about are all hard problems. Why C is a constant? It's a hard problem. Why probability distributions should represent particles are hard problems. All of these hard problems are the result of trying to justify a belief that really isn't justifiable. You get to a point where I believe this, but it doesn't make sense and I can't explain it, and it's a hard problem. So let's see, where are we here? If you get the proper viewpoint and the proper perspective, the hard problems disappear. Okay. Let's go on. Okay, now look at a top-down. Top-down logic. Next slide, yeah. Top-down logic. We start with the assumption of a fundamental awareness. Somehow, again, we have an assumption, that's our somehow emerging from random process into complexity, a process given credibility by mathematics. Then we allow the process of evolution to logically explain the physical, metaphysical, philosophical, and theological facts of the larger reality, including explaining much of the physical reality experimental data that cannot be explained by the bottoms-up approach. Thus, we come up with a top-down approach that explains the larger reality, our physical universe, and its mechanics, purpose, and function. Additionally, it explains our individual and collective connection and responsibility to that larger reality and to each other. The top-down approach generates a logical, scientific foundation that derives the wisdom collected and refined over thousands of years of human subjective experience, as well as contains all the contemporary physical science as a subset. So, these last orange words that I have here, I'd like to point those out. So the new facts enter the physical reality by a random draw from a probability distribution of these possibilities that are consistent with the rule set and all former facts. In other words, we have to have historical, can't have any problems in the flow and continuing history, and it has to abide by the rule set. Okay, let's go to the next slide, and I want to show you, I've talked a lot about pulling this random draw from the probability distribution, and now I want to give you a little sense of what I mean by that. So here's a chart that I generated, and I have a bunch of letters. I have A through Z, all the letters of the alphabet. Okay, each one of those represents an outcome. So there's 26 possible outcomes. So we have something's going to happen, and we have all the possibilities. There's 26 different possibilities that could come out of this thing that's going to happen. Okay, and if we look at all the letters here, A is 1, B is 2, there's 2 C's, there's 1 D, 1 E. You see these numbers up here are the number that's in the stack. Okay, this is probability now. So it's more probable as you go up here. So there's 25 chances that you get a K. There's 25 chances. So we have a total, if we count all those numbers up, if we add all those numbers up, we'll get 165. That's how many letters we have in this distribution. But there's only 26 different outcomes, but some outcomes are more likely than others. Okay, so the way this works is, say the A here is just 1A. That's all there is. You have 1A. That means there's one chance out of 165 that if you take a random draw, you're going to end up with A as the outcome. Okay, so some event, something's happened, something's gone on here, and we say, we don't know what it is. We're going to make a random draw and decide what we see when we make this measurement, what we get for the measurement. And so this then becomes the probability distribution. And you have to think of all of these letters, all the A, the 2 B's, the 2 C's, the 6 H's, the 25 K's, all these letters are going to get put in a box, shook up, randomized. And when you make a draw from this probability distribution, a random draw, you're going to reach in the box and you're going to pull out one letter. See, that's the random draw. All the letters, all 165 of these letters will go in there. So what's the probability you pull out a K? Well, that's bigger than anything else, right? Because there's 25 K's in the box. So your probability of pulling a K out is going to be a little bigger than your probability of pulling an A out, because there's only one A in the box. That's a probability distribution, and that's how that works. So this could be, any sort of thing. That could be the tree in the woods. What's the probability that we're going to see that dead tree in the woods? You see, if the tree in the woods outcome is maybe K, and the fact that there would be no tree at all might be H, and the fact that it might be a pine tree might be R. You see, there's all these possibilities of what we'd see when we go in and look at that spot. These are all the various possibilities. Put them all in a box, shake them up. We look into the woods, and when we do that, the system draws one out of the box, and that's what you see. So it's more likely you're going to see this K because, you know, that's probable for this woods. It's less likely you're going to see an A or maybe a Z or an E. That might be a pine tree in a deciduous forest. You see, it's not too likely you're going to see that. Or it might be a palm tree, you know, maybe way out here, you know, even a lower probability. You're going to see a palm tree in a deciduous forest. You see, that's very unlikely. So that's how it works. That's what I was talking about. All right, we'll go to the next slide. Hopefully this makes it a little more realistic than me just saying, oh, you take a random draw from the probability distribution. That's very, you know, that's very hard to see, but maybe this will make it a little easier. Okay, now here's some probability distributions. Here's a bunch of possible states that something could be in when a measurement's made. And you see here, the probability of getting anything other than F is 0. Okay, that's just like a 0 or 1. That's like the double slit experiment, and you've collected detector data, and you know that the particles went through a particular slit. What's the probability that it's going to hit the screen right behind that slit? 1. What's the probability it's going to go somewhere else? 0. So in physics, this is called a delta function, and it means it's a probability of 1, very narrow peak. Sometimes things are like that. There's only one thing it can be. So under the conditions, so that's what you get. Other times, you get real broad curves like this. Whether you get an E, an F, a G, or an H, it's all about the same. You may have an equal probability of selecting any of those out of a random draw. That's like the astrophysicist who points his telescope out into the outer space. What he might see out there may be 1,000 things that are all about the same probability that he might see out there. And he'll just get one of them. Probability distributions change over time. Right? In the double slit experiment, we had one probability distribution when we collected detector data. Then we erased the detector data, probability changed. Because the data available here to make the experiment consistent in history changed. So you can start with this kind of a peak over an F, and then just because of something that happens, you may end up with a peak like that over an I or a J. It could change. Or this may shift from here to something over here, where now these become not so probable, and something here around C becomes a lot more probable. Well, where these distributions are flat and not so steep, there's lots of things that come out, and this gives the system flexibility. Because if the system decides that what you need in your life, you're making a measurement. Remember, you walk into the bookstore, and the book your eyes go to that book, and you kind of think like, well, it's almost like that book jumped off the shelf into my hands. I really needed that. Well, if there's lots of variability in what can happen, the system has some room for playing, for manipulating in there, and nobody can tell. Here, if it tries to manipulate something and do anything other than F, it's obvious that there's a problem. Can't do that. But here, if it decides that a G is what you really need, it can manipulate that because nobody will notice. So if a system wants you to succeed, because if you lower your entropy, you're part of it, it lowers its entropy because you've lowered yours, then it will try to help you succeed. That's the basis of the synchronicity. So things change. There's lots of things that can make this probability change. Everything's connected. We're all connected. All this stuff in us, everything's kind of connected. What other people do affects you. What you do affects other people. So these probability distributions are very flexible. So that's one reason that these things change. Intents change future probability. But there may be 100 people that would like that future probability to be this way, and 150 that would like it to be different than that. So you have these intents pushing and pulling all the time. Probability distributions are very, changeable. And of course, the other thing is a random draw. If I'm going to take a random draw from under this curve, then I might get an A or a K. I may get something that's very unlikely, but it happens anyway. That's what we were talking about when we were talking about tunneling, right? We had all these particles in a box that it couldn't get out of, except 1 in a million or something that it could get out of the box, but we have billions of particles, so a whole bunch of them just keep coming out of the box. They keep teleporting from inside the box to outside the box, even though they don't actually have enough energy to get out of that box. They do anyway because they've got a distribution that has long tails to it. So odd things can happen. And odd things can happen when that astrophysicist looks out into space. Instead of getting one of those 1,000 things that are about the same probability, you may get something really off the wall that only was unlikely, but that's what you get. It still fits because he only has all the things that are in these distributions are only things that meet the criteria of the rule set, so they're all possible, and they meet the criteria of historical consistency. They're not going to create any, no pink elephants at the bottom of the ocean. So they have to be reasonable with a continuous history, and they have to be possible according to the rule set. But some of them can be very improbable, like the particle getting out of the box, and it happens anyway. So sometimes we get very odd things that happen. And that brings us to a conclusion that in a virtual probabilistic reality, almost anything can happen. So if you have a really, really weird experience, something really strange, is in your experience, strange things can happen here. You can draw things out of a probability that are very unlikely. All right. Now, one other thing I'd like to mention here. We talked about making the random draw, right? Well, what is that when we do that? Remember, we have a computer who's computing a virtual reality, and we have a player. The virtual reality itself is just data in the computer. Okay. The player does something. There's a consciousness that is animating this player. The player is animating let me put it this way, the player is animating the avatar. The avatar is virtual. That's my body. That's the avatar. But I get a consciousness that tells this body what to do. So the consciousness says, look left, and I do this. And the consciousness says, look right, and I do that. You see, because the consciousness says, look left, and that sends a signal to the computer that says, take that computer avatar, turn his head to the left, and then put data into the data stream of the consciousness of the player that shows what's left. That's me taking a measurement. When I turn my head and look left, I'm now taking a measurement of what's there. So the elf turns his head and he sees the lake. He turns his head over here, he sees the mountains. That's the measurement. So the player says, turn the head to the left. The computer sends the data to the player of what he's going to see to the left. Okay, that's the measurement. So it's just between the player and the computer. So the player looks at the screen of the double slit experiment. Says, I want to see what's on that screen. And the computer then is required to send data down that data stream to that player to show him what's on that screen. You see? And when the computer has to do that, the computer looks at all the probability and say, what's the probability of what's on that screen? Then it takes its random draw and it sends that data down the data stream to the player. See, that's how measurements are made. A measurement is first executed, is first created by the consciousness player saying, turn your head, look at the screen, open up a box, you don't know what's inside, open the box, dig a hole in the ground, you don't know what's under the ground. See, all of these are measurements, and every time the consciousness tells the avatar to look somewhere, do something, then the computer has to tell the player what's there in the virtual reality. And the computer does that by saying, what are all the possibilities that's there? What's the probability of these possibilities? Let me take one. All of them are possible. Some are more probable than others. And then that's what goes in the data stream. Okay, see? And now with that last chart, you can see how that's done, how those probabilities, you kind of get the idea of taking the probabilities of all the possibilities and just drawing one. But all of them are possible within a rule set, and all of them are historically all right too. There's not going to be any discontinuity. No pink elephants at the bottom of the ocean. All right, so that's how this works. And let's go to the next slide. We'll change a little bit. We've seen this slide before, but I'm talking a little bit about it differently this time. There are multiple virtual realities. Our universe is not the only universe. There are other universes, if you like, that are physical if you're in them. They're non-physical if you're not. So to us, they're non-physical. To them, we're non-physical. Physical and non-physical just being the point of view of the observer. There's lots of virtual realities that are not physical-like. Okay? And what's the difference between a virtual reality that seems very what we would call physical, because it's like what we experience is physical, and virtual realities that are not, more like the dream reality? It's the tightness of the rule set. How many rules are there? What does the rule set require on the data stream? Okay, so some rule sets may have nothing in them but communication protocols. So virtual reality, and the only thing that defines the rules there are communication. And that's a place where we don't really see bodies, we don't really see other beings. All we do is get information. It just comes back and forth to us. So we put out a, hello, are you out there? Can you tell me about such and such? And you may get something back. That's a virtual reality with those communication protocols. Or we have a virtual reality that has a lot of very tight, restrictive constraints for the rules, and we say, oh, that's physical, like this. So there's multiple physical realities with tight rule sets, and lots of, probably more, virtual realities with very loose rule sets. A loose rule set would be your dream reality. When you dream, it's not nearly the same tightness of rules as here. In the dreams, you can fly. In the dreams, you teleport. In the dreams, things just pop out of nowhere. It doesn't have a lot of rules about what can happen and what can't happen. It's a very loose rule set. And when you die, I go through it. Everybody likes to know about what happens when they die, so we'll do a little. I did a little run through that once, just trying to tell you what a free will awareness unit and how that worked, but we'll do it a little more detail this time. When you die, you lose your data stream from this virtual reality we call our physical universe. That data stream goes away because you're no longer here, right? Your sensors are no longer sensing anything. Your virtual sensors are no longer, when you turn your head to the right, you don't see the lake because you're gone, you're dead. You don't turn your head to the right, so you don't get data from that anymore, but you start getting data from a virtual reality. I call it the transition reality because it's the reality that people end up in after they've given up the data stream to this reality. The very first moments of it, you just become aware that you exist. Oh, what's this? Where am I? What's going on? Am I having a dream? What? So you have that kind of an attitude. And that quickly changes to you have I should say a need maybe, but you have an inclination, I need to go this way. And we visualize that in terms of moving often through a tunnel toward the light, but these are just metaphors. In a culture that never heard of tunnels and was always in the dark, they wouldn't have those metaphors. You see, they're just metaphors because of our culture. So a lot of the near-death experiences, people find themselves suspended kind of in space. They notice a light and they have this urge to move toward it. Well, that's kind of typical sort of thing. Often entities will come and meet you. Hello, welcome. Shake your hand, Uncle Fred and Susie Q will show up and say hello to you. And all of that is just to make you kind of relax and not be freaked out by it, just to, oh, okay, and very quickly, as I told you before, your sense of the life you just left starts to fade. You still have that, but it just starts to fade away. And now you're kind of engaged in this new reality frame with entities that seem to be friendly and everything seems to be happy. There's nothing scary going on. And they will say, well, come on over with us, let's come over here and I'll show you what to do. It's real simple, don't worry about it. Again, all of this is just to put you at ease, because that's the most important thing at this point, just to let a person, I'm okay, it's all right, and then the process can happen easily. The only problems you get is where somebody is obsessed, somebody is focused real tightly on something and they can't let it go. And then you have a little bit of problem with the transition, because you have to get that person to let that go so that they can move on. But for most people, it's not a problem. They very quickly figure out that they're someplace else, and it's sort of like a dream. Oh, so we'll just go along with it. Anyway, you'll get to a place, then they'll take you to a place, and depending on how relaxed you are and how ready you are to go on with this transition, they may do all sorts of things that are basically stalling and just go over there and see that line. You need to matriculate over there. There's somebody there that'll tell you what to do next. So you go over there and there's 10 people standing in front of you, so you stand in a line. Well, there's not really anything going on there. They're just buying time for you to relax and adjust. And eventually, with all this, standing in line and, taking the class and meeting other people and seeing old relatives and stuff, eventually you kind of relax and let go. And then somebody says, well, what do you want to do next? And you'll say, well, what is there to do? So, well, you can do whatever you want. What do you want to do? And you may say, oh, I want to go sit on a cloud and play a harp, but you probably won't. You probably will say, well, maybe I just want to chill here for a while. That's all right. You don't have to, you have free will. You don't have to do anything you want. Eventually, you get kind of bored with that. And it's like, well, I just don't feel like I'm doing anything. I'm just wasting my time. And, can I get back in the game? You see, it's that sort of thing. And they say, well, sure, we can help you with that. What would you like to work on? Now, if you're just new at this, and you've just maybe your second or third or 10th or 100th incarnation, it's mostly jump in, jump out. As soon as you relax, it's like, well, we got another slot for you, go, and it's that kind of thing. If you've been around the block a few times and you have certain things that you need to gain experience in and work on, then it's more considered of what kind of avatar do you need and what kind of situation to give you the higher probability of succeeding in the thing that you'd like to succeed in. You see, so you get to be a little more specific and picky after a while. In the beginning, you just need experience. Just get in there and have an experience. So let's say you've been around the block a few times and you are now going to pick another incarnation. You may get, if you need it, if you can benefit from it, you may get a little counseling session, if you will. And they say, well, what is it you think you need to work on? What really do you want to do? And you may say, well, I use this example a lot. I have anger management problems. That's my problem. I'm emotional. I get really upset and blow up, and then I'm sorry about it later. And I just can't seem to control that. And And they say, well, yeah, how bad was it? You say, well, it wasn't too bad. You know, just every once in a while I do that, but it is a little problem. And they say, well, you know, let's take a look and see. So now you get your life in Technicolor, right? And you get to see you interacting. And they'll show you all the things that you need to know to help you plan the next incarnation. And a lot of times people will say, well, I really don't have to work on anything. You know, I'm fine. I did really good. And no problems. And it's like, come here, let's take a look at this. Let's take a look at this and see really what happened. And then it's, oh, yeah, I remember that, you know, and you get a whole different perspective on your life at that point. And then you decide a good situation, and basically they help you with that. You know, you say, well, how about this and that? Is that all right? And you go, yes, because free will. You can always say, no, I'm not interested. You know, I'm going to go sit on the cloud and play my harp. You know, you can always say that. But eventually everybody gets back in the game because that's our job and that's what we do, and it's boring otherwise. So then you make an agreement, fine, and then you've heard the rest of the story. You know, your individual unit of consciousness partitions off a piece of its being level, not its intellectual level, and you know, logs in, puts in the password, and you get a data stream between you and the computer relative to that particular avatar. And then you start over with no intellectual information, but being level quality that you've earned in all the other incarnations. So that's kind of how it works. The transition reality frame is something that can be done very quickly if you don't have issues, if you're not obsessed, if you kind of already with the program because you've done it a lot, you know, you can do that very quickly. Sometimes it takes a longer time. Sometimes people are very obsessed with things, and it just takes a longer time for them to let go, a longer time for them to come around to get back in the game, or they were so, you know, traumatized that they have to take some time to unwind from that and to forget it all. So that's kind of what you should expect when you die. You will just become aware that you're in a different place now. And your first thought is, I'm dreaming, because it's sort of like a dream. But then things will progress. But that's your transition reality, another virtual reality with a very loose rule set that allows you to relax and prepare yourself for the next incarnation. So that's I get asked that a lot, so I figure I might as well tell you because somebody's going to ask me anyway how that happens. Okay, now, can you go to these various virtual realities? Can you visit them? Yes, you can. You are consciousness. Okay, you're a free will awareness unit, but you're still a chunk of consciousness. You're developing your own intellect and your own quality as you go, but you're still consciousness. You can travel wherever. Now, what does travel mean? Now, we think of having to get up and move someplace, right? Travel. That's not how you travel. You travel by connecting to a different data stream. Well, all these data streams are available to you from all the virtual realities, all the universes, even this virtual reality for transitions. All the data streams are there. And you pick a data stream with your intent. Where do you intend to go? And then you just let go of this data stream and start with that data stream, and there you are. You don't have to fly, you don't have to move, your consciousness. You just go from data stream to data stream, and your intent does it. Right? Well, how do you intend to do it? How can you intend to go to the transition reality if you don't know there is a transition reality? You see? That's the problem all explorers have. You know, they get to someplace new they've never been before. How do they know that there's fresh water, you know, halfway up the slope of that mountain, and that's the only fresh water around, and they're going to need water soon? How do they know that? They don't. You just explore. You have to start and just go, just do. And if you have no idea how to do that, you can ask the larger conscious system, show me someplace that would be educational, where I could learn something. And then it generally will happen. You'll be someplace. And then you have to find out what is it for you to learn there. You see? And once you've been there once, Now you can have an intent to go there anytime you want. So this out-of-body thing is a generic term, a very poor term because it has nothing to do with your body. Your body is irrelevant. Your body's just a data in a computer on a hard drive someplace. When we meditate, remember that yesterday we were meditating, I said the idea is to get to this point where you are just a point of consciousness floating in the void. You've let go of all the data stream, basically. Your data stream that defines what's going on with you in this world, you've let go of that data stream. You no longer hear, see, feel, smell, and if you do, you're not operating on it. If there are sounds like there were in the hall, it's not that you can't hear them, you just don't care about them. But eventually, the things you don't care about disappear. It's like when you're reading that book, and you're really into that book, and that book has your attention, and somebody walks through the room, or somebody beeps a horn on you, you never hear it. Why? Because you're focused there. You're not really interested in that stuff. Or if you hear it, it just, it's there, and you forget it. It's just non-operative. Well, this is the same way. When you get in that point consciousness state, guess what? You already are out of body because you've let go of the data stream that defines this reality. You're not in this reality anymore. But you haven't yet made an intent to pick up any other data stream. So you're just a point of consciousness floating in the void. So from that point, you can do all sorts of things. Go someplace, see something, data from a database, different reality frame. Your intent can take you there. The intent has to be clear. It has to be, again, you're querying databases. You have to be specific. But practice then makes perfect. And the more experience you have, if you're an explorer, then the more you get to map the territory. And pretty soon those explorers found that freshwater supply over there on that mountain. They found a lot of other things too. They found a place where there was food supply. And how did they do it? They just went out and looked. That's how they do it. You just go out and say, well, what's over here? What's over there? Take me someplace, useful, someplace where I can learn something. If you say, take me someplace that's fun and entertaining, probably not much will happen. The system has no interest in entertaining you. But if it's someplace where I can learn something important, then the system is interested in you learning. So that's how we explore the larger conscious system, by letting go of this data stream, which means point consciousness, and then using our intent to connect to a different data stream. That's out of body. That's remote viewing. That's lucid dreaming. These are all just different techniques to get to that same point to where you've let go of this data stream and you use your intent to get another. So all of those things really are the same sort of thing, just approached with different techniques and different belief systems. So so there are multiple virtual realities out there, many of them, of all sorts. And I encourage you to explore them. And in the beginning, I encourage you to explore those that can give you evidential data. Because if you explore those that don't have evidential data, like this transition reality, you might find it interesting, but you'll never answer the question of, am I making this up? Or is this coming to me from a data stream outside? Because see, your consciousness also creates data. Your consciousness can create data. So the consciousness system creates data in the data stream, sends it to you. You create data and send it to it. You also are a creator because you're a piece of consciousness. We call that our imagination when we create the data. Well, that data is intermixed with any other data if you don't have good control over your intellect. See, that's why we have to say, let the intellect go. Because if your intellect is yammering and talking, then you get a data stream that's talking, and you're getting data, and you can't separate the data, because data is data. You're just getting data from multiple sources. And if you get data from multiple sources, it's confusing. You don't know who's doing what, and it all gets mixed together. And then you get your ego involved in it, and you start interpreting the data because you're frightened You interpret that data as a three-headed monster with big teeth, you see, because you're afraid. Not because there's really a three-headed monster with big teeth out there, but you're frightened and you hear something and it sounds like a growl to you and suddenly you see a monster. Well, that's your data that you're creating based on your interpretation because you're frightened. So you see the problem here? What you see is what's out there coming to you and what you are that are feeding your own data to the data link. And the only way to separate those two is with practice. You just have to just keep doing it. And in the beginning, you won't have a clue what you're doing. Because it's like the explorers that first land on new shores that nobody knows anything about. They have not a clue what they're doing. They don't know what direction to go. Every direction is just as possible as any other, to be good or bad. You just go. Most of us have a problem with just going because we have this sense of control. If I'm not in control and I don't know and I just go, it could be really bad. I may go over there and I step on the other side of that rock. It might be a den of rattlesnakes. It might be a hungry bear. Who knows? So I'll just stay here at the ship and on the beach because that's safe. You see, most of us feel that way because it's the unknown scares us because it might be bad. So we don't explore. You have to have the courage to just say, well, I don't know, but here I go. And what'll happen will happen. So that's have the attitude of an explorer, have the attitude of a scientist. No preconceived notions of what you'll find, just do it. And if you're open like that with no preconceived notions, and if you don't have the fear, then the data you get won't be so polluted by your own fear and your own imagination. So that's how we learn to meditate first, so we can tell the intellect to sit down and be quiet. It's like an unruly child, right? Just sit down and be quiet and let me be open to what comes. And if you try too hard to go out and grab it, it will elude you. You need to be open to what comes. You can have an intent for data, but then you just open and get the data. You can't pursue it. It's not like you can go out and grab that data source and own it. You can't. You're querying a database. It'll be sent to you, you just accept it. And you'll say, am I making this up? Well, 2 or 3 years later, and you've done this 100 times, you'll be able to tell whether you're just making it up. You'll be able to tell the value of the data. See, the data will have value or not. So after doing this for 6 months, say interacting with non-physical entities or going places and doing things, if after 6 months it's time to do some judging now, tell that intellect to wake up and get back to work, and you look at this and you say, has this been valuable? Am I learning something? Is it, am I better off for having done this? And if the answer is yes, well, keep going. If the answer is no, then let it go. Do something else. When you get to that question, is it valuable or not to you, does it matter where it comes from? See, at that point, it doesn't matter. Is this me or is this it? Well, if it's it, and it's a data stream from outside of you, but it's useless to you, let it go. If it's good information and it's valuable to you, but it's coming from you, well, go with it. You see, it doesn't matter where it comes from. What matters is it valuable? Can I use it? Am I growing with this data? Am I getting a better sense of reality and how it works? Am I solving my problems? Am I growing up? And that answer, be it yes or no, doesn't depend on the source. The source is irrelevant. So see, this question, well, was that me or was that something else? That's a question that comes out of our fear. The fear is, am I being a fool, talking to myself, or am I really doing that thing, talking to some being out there? I don't want to be a fool talking to myself. I want to talk to that being out there. So immediately you start questioning. It's the wrong question. The question first is, let me just experience until I get enough data that I can evaluate it. You can't evaluate hello. You see, you hear somebody some kind of opening, first, it's 3 thoughts. You can't evaluate that, where it's coming from. Because all data, you just get data, no source. Doesn't get tagged with a source. So this is what you are up against as an explorer, and this is why most people don't do very well with it. Their ego gets in the way. Their intellect gets in the way. They get confused, and they have this burning need to know what they're doing and to judge it immediately, and they have this burning need to control, to make sure that they don't get hurt, or it isn't bad, or they're not foolish, or they're not wasting their time. So right from the beginning, they want to control it, but they don't even know what it is. So they're like the explorers who get to the beach of the new land and then can't get off the boat because they're afraid of what they might find. You see? You just have to have courage and go on out there and be open, and you have to be able to let that intellect sit down and be quiet so you can get data. Otherwise, you're going to overwhelm the comm channel with your own yammering intellect. You can't hear anything else. All you can hear is yourself. So that's a little bit about multiple realities. Maybe that'll be helpful to you. Okay, next slide. Let's see, we've been here too, but I have a few other points I want to make about this. Here's where I talked about the virtual reality, our virtual reality, not somebody else's virtual reality, but our virtual reality here called the physical universe. This virtual reality has some structure. Okay, in order for consciousness to run this virtual reality as a schoolhouse, it has to keep track of where it's been. How can it maintain historical consistency if it doesn't know what historical is, right? So it has to keep some historical data because it can't run the show without it. How can it be prepared for the new data stream if it doesn't keep track of where we're likely to be going, what the probable future is? So it has these databases. I'll tell you again because this was some days ago that we talked about this. So our virtual reality has a structure that includes probable future, which is everything that could happen, all the possibilities, and the probability that it will happen. So it looks like more of those probability functions, those statistical distributions. It's like that. And the way it works is it says, okay, here we are at this delta t. What's probable for the next delta t? Well, it says, all right, here's probable. I just expand out from what I know now and the history of all these entities and what they do and the kind of choices they make. I'm going to take a guess at what's going to happen in the next delta t. Well, that delta t is only 10 to the minus 44 seconds away from where we are now, so that's pretty easy to guess, right? In that short amount of time, it's not too hard to figure out what's going to happen next. Not much. It's going to happen different than it is right now in that much time. What do you move? A billionth of a centimeter or something, so it's easy. And then they say, well, given that guess was right, I'm gonna extrapolate that out to the next delta t and see what was likely to happen there, and the next and the next. So one at a time, it can extrapolate out. Well, of course, it's not always right, and it goes out far enough, it gets kind of ratty because now you're having guess on top of guess on top of guess, and if some person with free will does something unexpected that wasn't in there, some pulls something out of the tail of a distribution instead of out of the most probable part, then it changes. Well, then the system has to go back to that change and then reprogress from that point on. But most of the time that doesn't happen because we're pretty predictable, particularly if you have a history of us, and not just a history of where we've been or the history of what we've done, but the history of every feeling, every emotion, every choice, every thought, us in our entirety, down to the core, us, then we're pretty easy. So 90% of the time, or maybe even 98% of the time, it's going to be getting it right. And some of the time it'll get wrong, but the further out that it progresses this probable future, the chancier and the rattier it gets. So if it wants to go out 10 years from now, it's doing a lot of guessing. If it wants to go out 50 years from now, this, I'd take that with a grain of salt, because a lot of things could change between now and then. There's a lot of free will going on between now and then, but at least that's what it looks like at the present moment. So that's what this future probable database looks like, and this is the database that we change with our intent. We shift this probability around with our intent. All right, well, we've kind of talked about that before, and well, let me do the other part. As time goes by, delta t is in the present. It's right where we are now, right at this moment in time. In this particular delta t in this simulation, right, where we're talking about our avatars. And our avatars are what produces constraints on the data stream that's being sent to us, the consciousness. Go back again over that. When we go to the next delta t, that last delta t becomes past. And then we go to the next delta t, that one becomes past. So you see, as we move through time, every delta t, that future probable database is turning into a past database of all the things we could have done and the probability that we might have done them. And through that past, there's a thread traced through that history of what we actually did, the choices we made. And that would be our history thread through the database, through the past database. So that's the kind of data that's available. All right, now we talked about healing with our minds yesterday. Well, what are we doing when we heal with our minds? We're modifying the probability of that illness. We see something, we see an illness. We're using our mind. Somebody has a tumor. Okay, they have cancer someplace, and we visualize that cancer. We use a metaphor of white and dark, and in our culture, dark is always the bad stuff, and light is always, the bad cowboys wear black hats, and the good cowboys wear white hats. It's just a cultural thing with us. So dark is the bad stuff, light is the good stuff. We send white light on it, and all of that is just metaphors to help us focus our intent on modifying future probability of the outcome of that illness. We want the probability to be that that tumor shrinks and shrinks and shrinks and goes away. That can happen. And why can that happen? There's a lot of uncertainty about what tumors do. Sometimes they grow, sometimes they shrink. Sometimes they go away, sometimes they get worse. Lots of probabilities. So we look at that probability distribution that we saw. Remember those curves that went like that? Well, there's some part of that curve that says it goes away. It shrinks and shrinks and goes away. And there's another part that says it grows and grows and becomes fatal. And we're trying to make the part that shrinks be more probable, right? Make that peak higher, and take this peak that says it, is fatal, make that less. We're trying to change the probability here of the outcome, so that when the measurement is made, which means the person's health goes on, right? The next day comes, and they wake up. Do they feel better? Do they feel worse? We get a new measurement made. Well, when the measurement's made, it's going to pull random out of that probability. And if our probability of them being well or being better is bigger than the probability of them being sick, then it's more likely they'll have to draw out of the probability that's better. They still might draw out of the probability that's sick, but it's more likely they'll do it when the probability is better. So that's how we heal with our minds. When we remote view and see something someplace else, we want to go to some other part of the world and see what's there. What we're doing is looking at that data in that database. We're looking at the database of the near past. Well, the near past is really near. It's only, 10 to the minus 44 seconds past, which is still pretty close to the present. So when we go in remote view, we're saying, well, what's there? And you could go to that database and say, well, here's what's there. We're just collecting data out of the database. Now, why do remote viewers have these double and triple blind protocols? I don't know if you know much about remote viewing, but the way remote viewing works is they have person A picks a lot of sites to remote view, test sites, and they write them down and put them in an envelope. They write maybe the coordinates down, put them in an envelope. They give these to B. Person B gets them and shuffles 500 envelopes up that all have test sites in them, and again, puts them in the box, shakes them up, and then they take them over to person C, who's running the experiment. Person C reaches in, pulls one of those envelopes out, and walks over to the remote viewer and says, I have a location here, tell me what you see. The envelope's never opened. The remote viewer's never given coordinates or anything about it. It just says, I have coordinates in an envelope, tell me what's here. So now we have a triple blind experiment, and that helps the remote viewer remote view successfully. You think maybe that's making it hard for him. Don't even let him touch the envelope or anything else. It's triple blind. But if you gave him any clues, if you told him the coordinates, his intellect would jump into it and say, oh, coordinates, let's see, that's about, it should be over here, maybe about Central Africa, maybe up a little bit, okay, pyramid, right. I see the pyramids, you see. And with that data now being mixed with the data that he's getting, he gets confused. So the remote viewing protocols are so tight to help the remote viewer actually do a good job. Because all the remote viewer has to do, I want to see the place that's represented by the coordinates in that envelope. Well, that's a unique address. There's only one set of coordinates in this envelope, and he's asked to see them. That's good enough. The system knows that envelope. It's a virtual envelope, right? With virtual writing in it about its virtual reality. The system's playing all ends of the game. The system knows what's going on, so the system knows what that is, and that's it. I want to know what the place is that's designated in that envelope in that guy's hand right there. Well, that's good enough, so they get that information. So the way remote viewers work is to have protocols that prevents their intellect from getting in the way. That's why it's easier for you to heal and work with people if you're doing your experiments with people you don't know. If it's somebody you know, then your intellect is more likely to get involved in it. Eventually, if you can get that intellect to behave, you get that naughty child to sit down and be quiet when you ask it to, then you won't have those problems. Then you can work on yourself, you can work on your relatives, you can work on your children or other people you care about, and your own ego won't get in the way of doing that. But up until then, it's just easier and more productive to work on things that you have no idea what the result is and then find out the result later. Get evidence. Evidence is what will convince you that this is real. And after you get convinced it's real, there's not a whole lot more point to it, I guess, unless you just have somebody you want to help. Because that's the whole idea here, is to get your own experience with the larger consciousness system. So your left brain gets satisfied that you're dealing with a real thing. Okay. Let's go on to the next. This is a little cartoon of that probable future reality. Okay. This is time. Time starts at the center, so t equals 0 is right there. That's now. Okay, that's now. And then these are probable futures that are further and further out in time, and out here maybe like 10 or 20 years or 50 years or something, and in there is now. So out here this is all out at, say, let's just say 10 years, and this is all now. So you see that there are some things that are out here that are pretty big, that are out here maybe 5 years, 8 years away. It's pretty likely that's going to happen. Why? Because of the way we are, the way our culture is, the way things have been going, it looks likely that's where we'll go. On the other hand, there's lots of blank stuff out here too that could go anyway. The system has no clue what might happen there because it's very volatile. And out here's one that's way out that's really big. So if you were a prognosticator looking at what's likely to happen in the future, that would be a pretty good bet. Something out there is very probable. But notice as you get in toward the center, there's lots of tall curves. So it's only about what's going to happen an hour from now. Well, the probabilities get really big because that's easy to guess. It's more accurate. So they get bigger and bigger as they get in toward now, and they get fewer and sparser and not too big as you get further out. But this is kind of a cartoon of that future probable reality. It works something like that. And you might think of this whole surface of this dish or this plate, think of that of maybe being like a cloth, and you have a little bit of it sticking through a hole in the center, and you're just pulling it down, and all those probabilities are coming in like this and just disappearing into the middle. And what happens is they come out the other side as past probabilities, you see? So that's the image. So they're all sitting there, and they just slowly, this whole map works toward the center from all sides, and it disappears down the pinhole at the middle, and then reappears out the other side as the past probabilities. You see all the things that are possible, and the probability that they might actually happen, and then all the things that are past, and the probability that they could have happened, along with a history thread of what did happen. So maybe that visual will give you a little more sense of what I'm talking about. Okay. Now we can look at things like, well, there's lots of things. We can look at things like the placebo effect. How does that work? Changing future probability, right? You give somebody the idea they'll get better, they'll help them get better, because now there's positive intent there. They'll feel great, I'm gonna get better. I got this really great medicine, brand new, just in time for me. And you feel good about it, you're likely to get better. In general, people who are positive don't get sick as much. People who are positive and real positive attitudes have a lot of very positive experiences in their lives. People who, oh, everything happens to me. I mean, you know, I just got over this illness, and I got another one, and my plane got canceled, and the taxi driver was drunk, and everything just happens to me. Well, it does. Those people, everything just happens to them, and if you listen to their life, it's just a sad story about all the stuff they've had to deal with, but they create that, you see, because of their attitude that's created. So if your life isn't really full of joy, then go look in the mirror for the cause, you see. That's why it's probably not full of joy. It's what you're creating. People, yeah, we can go to the next slide. People talk about sometimes the law of attraction. You've probably heard about the law of attraction. That's an idea that you can, quote, program the universe, unquote, to give you what you want. Well, there's a little truth in that you can modify future probability. It has nothing to do with the universe. It has nothing really to do with the program. It has just to do with you modifying future probability. But there's some constraints there. One of them is that this is a system that's trying to help you succeed in becoming loved, grow up, to lower your entropy. And if what you do with this intention is to create more fear and a bigger ego, then you're working against the system. And often the system will teach you a lesson when you do that. So yes, you can program things and your life will change. This thing with modifying future probability, you can do it for good or for bad, either one. It's it's sort of like the gun, you can use it for good or you can use it for evil. It's not the gun that's good or evil, it's the person using it, It's the intent that's important. The system will try to shift probability the way your intent is, because that's the way it works. It's feedback for us. So if what you want to do is make people sick instead of making people healed, you can do that too. What do we call that, right? Voodoo or something like that, right? Where you want to make people sick. Pay me money or I'll make you sick, you see? That happens too. That's a very real thing, and is in some parts of the world, that's a very common thing. So it's it can go either way. That's why you make your fears come true. If you're fearful, you tend to manifest your fears. And you've probably seen Dr. I think it's Masaru Emoto freezing ice crystals. He freezes ice crystals. He has a freezing machine. He puts the water in, and as the water freezes, he plays nice music, and he gets pretty crystals. And he plays music that isn't nice, and he gets ugly crystals. And he thinks, well, I shouldn't say he thinks, the way it's written is that the water likes Bach, but doesn't like acid rock. Well, it's not that the water has musical taste. It's that Dr. Emoto has musical taste, and his staff has musical taste, and their intent is what's making those ice crystals, freeze pretty or freeze ugly. It's not that the water. So we then think that water is conscious and has preferences in the music. You see, it's not that way. It seems that way, but it's not that way. So there's lots of things like that. You can use your intent. Paralabs uses intent to bias random numbers, and a little later we'll talk a little more about that. They'll have a random number generator, and they'll generate random numbers, and they'll use their intent. I want the average of this bunch of random numbers to be less than 0.5. Let's say it's between 0 and 9.9999, 0 and 10. The average is going to be a half. 0.5 is the average. And if you do 100,000 numbers, you'll get something like 0.5000001 or 0.4999999. If you do enough numbers, you'll get real close to that 0.5. And they'll use their intent and make sure that it's always 0.499 rather than 0.5001. And they can do that 100 times in a row, to where you have 100 random number generators. Every one of them is a little lower rather than a little higher, whereas normally some equal numbers should be lower than higher, right? You should have equal numbers of those because it's just a random event. They can change the result of the random number generators. Intent can change anything. You're ill, you have issues, you want to help someone, you want to change yourself, you want to get rid of your fear. Intent. You want to find your ego, anything you want. You want to go out of body? See? What do you want to do with your life? But if it's something that puts you on the path of growing up, you'll find the system will help you. The larger conscious system will say, okay, a little nudge, a little boost, the book jumps off the shelf right in front of you. Ah, that's what I needed to know. That's my next step. Synchronicity, things will work for you. If you're working at odds against the system, you're de-evolving, you're feeding your ego, then not so much. You're not going to get nudges that help you. You can still do it, but the system isn't going to participate. Okay. Well, one other thing I should say is that when I say you can change probability, there are limits. Okay, when you change random numbers like they do at Paralabs, there are limits. You can only change the random numbers within the bounds of natural uncertainty. Okay, same with that cancer we were healing. Okay, there's a cancer, somebody has a lump on them, and they haven't had it diagnosed yet. It's just a lump someplace. This is a lump on their neck, say. And they tell you about it, and you make an effort to try to heal that lump, make it go away. It might be cancerous, might not, they don't know. Well, it's much easier for you to heal that at that state, you see, because there's a lot of uncertainty what that lump is. It may just be swollen lymph glands. You see, you don't know what it is. So you have a probability distribution that's one of these wide things like that. It's just as likely to be a lymph gland swollen as it is a tumor. So it makes it a lot easier to deal with. Okay, so then they go and have a biopsy, and the biopsy says it's cancer. And then they say, oh, I'm going to get another biopsy to check that. So they go get a different biopsy. Oh, it's cancer. And then they go and they tell their friends, I got cancer. And all these people feel really bad for them and so on, and they're terrified themselves because this is cancer, and I've only got so long to. Now you can have. They come to you and they say, can you heal me? See how much harder it is now. Now they got one of those curves that looks like this over going to die soon, and there's not so much uncertainty in there anymore. So it makes a difference how much uncertainty is in the problem as to how easy it is for you to modify those probabilities. Now that doesn't mean never go to a doctor. You see, what it means is do your work early on. Don't wait till the diagnosis is final and you've had your 3 doctors tell you, that it's cancer before you start taking measures to do something about it. That's the key. When you have a lump, yes, you need to go see a doctor and you need to go have that checked. But the work that you're doing on it should have started long before. Matter of fact, it should start now. You should exercise. You should get more rest. You should eat good food, get rid of the junk food, right? It should start now. Now's when you can modify the probability of, health problems 5 years from now. Well, there's a lot of uncertainty in what your health is going to be like 5 years from now. Huge amount of uncertainty. That's pretty easy to modify future probability there. But if you wait until you get a diagnosis that's very unpleasant, hard to turn around, now it's a harder job. So I'm not suggesting that you don't go to doctors when you have medical needs. I'm suggesting that you don't put everything off until it's crisis. The management by crisis is a bad idea, particularly when it is about your health. Start managing it now while it's easy to manage. Using your intent now. And somebody, if you're helping somebody, if it's your child or your parent or your friend, and they have something that doesn't feel right, that's the time to start working on it. Not just forget about it until they tell you what the diagnosis was. Start working on it then. Same with yourself. So that's the lesson there. It's the uncertainty that makes these things possible. So when they're looking at a random number generator, they're not, and the average is going to be 0.5, they're not going to make that random generator that has, say, 10,000 random numbers in it, they're not going to make that random number generator go to 0.3, you see, or 0.8. It's too big. The uncertainty, there's a certain amount of natural uncertainty there. Could be 0.499 or it could be 0.5001, right? And they expect that much variation. So that's where you have the ability to move it, is in that third decimal place. You're going to change things in that third decimal place. And that's all you're going to change it. You're not going to change it to a 0.3 or a 0.6. It's outside of what the rule set says is reasonable. So here's that little bit of uncertainty, and I can make that shift. And Pear Labs doesn't understand how reality works, and they were very frustrated with that because they could only make these little changes. Changes are real small. So they never had these big effects that would, that they could go publicize, or little effects. Which the thing they did understand was that if you can have that same little effect a whole lot of times, you got 20 random number distributions, and all 20 of them are to the low side. That's the same probability of flipping a coin 20 times and getting heads every time. Well, it's 1 in millions, you see? So it shows you a very dramatic result. It's a tiny little difference that isn't too impressive. That gets us to a concept called psi uncertainty principle. The psi uncertainty principle is based on this same idea. You can only affect things within the natural uncertainty around those things. That's because it's a rule set problem. Remember, what we get here in this virtual reality has to be consistent with the rule set. Well, to be consistent with the rule set, it needs to be within the rule set's uncertainty for that. So if you give 100,000 random numbers, the rule set says that they're only going to vary by so much at certain decimal place. Well, inside of that uncertainty, you can make changes. Outside of that, you're doing something that violates the rule set. So that's psi uncertainty. Your psi, your ability to change things, to modify reality, has to stay within the uncertainty in the rule set. And what that turns out to look like, if you kind of make it less technical, is that there always has to be plausible deniability. It's a legal term, plausible deniability. There always has to be plausible deniability that you've done anything at all. You see, if you looked at if you just had one bunch of random numbers and you said, look, I wanted it to be less and it's 0.4999, it is less. The system says, well, so that could have happened anyway, right? Plausible deniability. But what you have to show is that I can do this n times in a row. And now you've shown something very, very unlikely to have happened. But each particular instance falls within the plausible deniability because it has to fall within the uncertainty natural to the problem. So that's how these things work. All right, let's go on. We've gone on to that's not what's in my thing. What time is it? It's time, is it time for a break? 9, 10, 11, yeah, it's probably time for a break, right? So let's go take a break now.